Let us next define this new function capital F in terms of our already defined function mu, like this. For any positive integer n, let capital F of n be equal to the sum of the mu values of all the positive divisors d of the input n. And now let us see what the values of capital F are. We first see what f of 1 is. F of 1 by definition is this. Now what are the positive divisors d of 1? Only 1. So that means this sum reduces to this mu of 1, which by the definition of mu is equal to 1. Next we are going to see what capital F of n will be, can possibly be if n is greater than 1. So next we consider our n to be greater than 1. So it will then have a prime factorization by the fundamental theorem of arithmetic. Let that prime factorization be this, where the primes pi are distinct and each exponent ki is a positive integer. Let us first see what happens to f of p1 to the power k1, this prime power in the factorization of n. By the definition of f, this is equal to the sum of the mu values of all the positive divisors of p1 to the power k1, and those positive divisors are these 1 p1 p1 square all the way up to p1 to the power k1, and then we apply the definition of mu to each one of them. Mu of 1 is equal to 1. What about mu of p1? P1 is a square free integer, in fact it's just a prime. And how many primes are there in the prime factorization of p1? 1, and that is p1 itself. So by the definition of mu, this is equal to minus 1 to the power 1, that is minus 1. The other powers, higher powers, however, none of them is square free because each one of them is divisible by p1 square. These other powers may actually not be there. However, whether they are there or not there, it does not really matter because by the definition of mu, all their mu values are going to be 0. So ultimately we are getting 0. Now next we recall our recently proved result, theorem 6.5, which states that mu is multiplicative. By that fact and by the way we have defined capital F in terms of mu, it follows from theorem 6.4 that our f is also multiplicative. So f of n would be equal to this product, f of the individual prime powers in the prime factorization of n. And we have just now shown that this is equal to 0. So similarly the others will also be 0, but we need not even know that because the product has now become 0. So how can we summarize all these things? So we summarize our discussion in this theorem 6.6. For any positive integer n, the sum of all the mu values of the positive divisors of n is equal to 1 if n is equal to 1, and it is 0 if n is greater than 1. And finally we have in this theorem 6.7 our Mobius inversion formula. It is because of this result that the function mu has been defined. In this result there are two number-theoretic functions, capital F and small f, and they are related to each other by an equation of this form. Capital F of n of course is a positive integer, any positive integer, equals the sum of the small f values of the positive divisors d of n. If so, then we can invert, we can interchange the roles of capital F and small f like this. Small f of n then equals this sum, where each term now looks like this, mu of d times capital F of n divided by d, as d varies again over the positive divisors of n. So you see that in this inversion, very mysteriously mu is involved. You go through the proof that's available in the text and try to figure out exactly why this happens. And whatever doubts you have, you write in the comment section below so that we can have a discussion. Now as d varies over all the positive divisors of n, so does n divided by d, and that is why you can write d here and n over d here. You will get the same sum ultimately. Now how would this inversion look if we apply it to the similar formulas for tau and sigma? Let's see. So let us go back to our tau and sigma. Tau of n is the sum of that many ones as many positive divisors n has. So that way we get the number of positive divisors of n, and sigma of n is the sum of the positive divisors of n. Now we know that the constant function 1 is multiplicative in a trivial manner, and the identity function d, whose input is d and output is also d, where d is any positive integer, is also multiplicative in an equally trivial manner, and so are tau and sigma. So that means we can apply our Mobius inversion formula to these two equations. The first equation gives us this: the constant function takes the place of tau, and tau takes the place of 1. And of course, to adjust things, we also have mu involved here. So in this very strange way, the right hand side, no matter what n is and what its positive divisors are, is always equal to 1. And from this second one, we get that. Now this is not the constant function, sorry. The identity function d takes the place of sigma, goes over to that side and becomes n, appears as n. And sigma takes the place of this one. So it appears as sigma of d, and of course you have mu of n divided by d. So regardless of what n is, this sum is always equal to n. Or you may interpret these things like this: n can be written as a sum like this, and 1 can be written as a sum like this. Now besides these things, there is one more thing in this section. Say you have two number-theoretic functions, capital F and small f, so that capital F of n equals the sum of the small f values of all the positive divisors of n, the kind of relation we have been considering. Now you already know that if small f is multiplicative, then so is capital F, by theorem 6.4, if I am remembering the number correctly. But what if capital F is multiplicative? Can we also conclude that small f is multiplicative? If so, how? So these are some further things that we will discuss, but not today, next week. So see you next week with those new things. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.